Before I actually start part 3, I wanted to review some things in part 2 because I remember our time being somewhat cut short by necessity. And so I wanted to ask the audience and any participants if they had questions, comments about what we've covered so far. So I'm not going to go through a summary of what we've covered so far. I'll let you I'll let you think of that. But if you have questions about this diagram or about one of the, some of the things we've covered so far, I mean, the most important thing is that you're comfortable with this diagram. You're comfortable with this diagram, which is kind of similar. And of course, you're comfortable with this diagram. So long as you're comfortable with these diagrams, you know what they mean, then we're good. And maybe the hardest diagram we did last time was, of course, the homotopy type of block 3, which was this diagram. So if anybody wants to ask questions about these diagrams, then please, by all means, or other questions.
So Martin, I have a question about this.
Yeah.
I think I understand the topological claims you're making, but I'm still trying to connect them up with the physics. So if I consider an observer who necessarily will be highly accelerated, who threads the ring singularity, so they're moving from kind of the way it's sometimes split from our universe into the anti-universe. How should I understand that with regard to the topology of the two spheres joined at the poles? How does the observer traveling through the ring singularity experience or see that that's the topology, or can the observer see that?
That's a very good question. That's a very good question, and I'm gonna unpick that question somewhat, because that's a really very nice question. So first of all, of course, the diagrams I just drew are t equals t constant snapshots of the solution.
Exactly. So like what point does that observer puncture through these surfaces?
Yeah. So as we'll do today, I'm going to spend 2-3 minutes on your question because I think it's important. But as we'll do today, we'll understand what I'm about to draw in more detail. But this is block 2. This is block 3. Now, as Jacob asked last time, he said, should we trust the Penrose diagrams? And of course, I told him, well, yes and no. I mean, the causal structure to some extent you can, but of course, the topology you can't, because in a Penrose diagram, every point is an S2. The idea being, the models being Schwarzschild or Minkowski, where spherical symmetry is a legitimate assumption, which reduces the number of variables from 4 to 1, from 4 to 1 plus 1, or 3 plus 1 to 1 plus 1. But of course, in Kerr, once you pass block 2, so once you pass R equals R negative, R equals R minus, where R minus is comes from the root of this guy, which I defined in previous talks. Once you pass this, then of course the topology looks more like this, right? So you're in this region where you have these spheres, and then eventually you hit a ring. And the ring sits at R equals 0. And then once you pass R equals 0, you can, the solution's perfectly regular beyond that, apart from the ring singularity, where there's, divergence in the Kretschmann scalar that goes like 1 over R to the 12, but only in specific directions. So specific contractions of the Kretschmann along this ring. Of the Riemann tensor along this ring. The Penrose diagram is of course not too useful. Well, it is in a way. So let's let me now do something that's quite common in Wald or some of the other papers like Hawking and Ellis or whatever. This here will be R equals 0. And so this is a dashed line because it's not you know, it's not a sphere, right? It's an S1. So this really is R cross S1. And my way of representing R cross S1 in the Penrose diagram is a dashed line, which is not faithful, of course, because, you know, I can't draw this in this number of dimensions. And so if I understand correctly, Eric's question, you know, you could have some observer that goes through here, but then that decides to pass through the ring. And as you can see from the causal structure, you know, if this observer doesn't suddenly switch off their rocket and lie in the equatorial plane, then it will continue to avoid the ring, and it'll just pass through, and it can squiggle around the ring as many times as it wants, and eventually leave the ring. So this is a perfectly reasonable trajectory. And Eric's question, I believe, is what does the observer see when they're going through this this path or this motion?
They're going above or below the ring?
Yeah, exactly. Right. So exactly. So I could draw this, you know, I could draw this in a different way. I could draw it like this. There's the ring. Right. And then what the observer is doing here is they're passing through R equals 0. So they're going, say, into, so this is the locus of the ring, is this R equals 0 sphere, if you like, or the union of these two hemispheres. Right. And then this observer, so the colors are misleading. Let me change colors because I drew the ring in blue. So let me actually be faithful to the diagram above. I've used red this whole time, so this is a bit of heresy. My apologies. Okay, so there we go. So I'm an observer. I go into the ring, into the R equals 0. But I can perfectly leave the R equals 0 hemisphere. And then, you know, this is a T equals T constant snapshot. So later on, right, later on, there's another ring. And I can perfectly go back, you know, outside and back into the ring. Right? So there's no problem with an observer doing this, and in fact, you know, from the point of view of the Lorentzian geometry, you could say that the path light cone of any point in block 3 contains past incomplete. Let's see, past incomplete. Let's see. Right, so the only incomplete geodesics are the equatorial ones. So if, you know, this is, I suppose, the confusing thing, or the non-trivial thing is that, you know, suppose this is the Kerr axis, you know, if the observer, if I'm probing the observer at some point here, I want to consider the past light cone of this point, you know, strictly speaking, there are no geodesics that are incomplete that emanate from this point, because the only incomplete ones are the ones, apologies for this mesh of colors, the only incomplete ones are the ones that lie in this equatorial plane. So you know, it's not such a bad singularity, you might think, right? Because a curve would have to be here, and then it would be, in order for this curve to be incomplete, I would have to suddenly stop being this curve, and I would then become a time-like or a null geodesic. I mean, in this case, it's an observer, so a time-like geodesic in the equatorial plane. So I would, you know, there's a great amount of fine-tuning for me to say that a curve from this point P ends up being past incomplete, because in order to organize that, I would have to get to the equatorial plane, switch off my rocket, and become a time-like geodesic in the equatorial plane. But that process will have to be extremely.
Can there be any path that intersects with the ring? Does it have to come in through the equatorial plane? Couldn't it just?
Yeah, so absolutely. This is a path that you know, hits the singularity, and you can't extend this, but this is not a geodesic. So, you know, that's, yeah. Yeah, so I mean that's the picture. I mean, you know, you can thread the ring singularity as many times as you want. By as many times as you want, that's not quite true. Of course, there's a proper time that will be spent. You know, if your acceleration has a bound, as an upper bound, then this curve never gets close to null. This curve never gets close to null. So it never goes like this, right? It stays kind of relatively vertical. And then there's depending on the acceleration, the upper bound that you have for the acceleration of the curve, there's a finite number of times that you'll be able to thread the ring, right? In the whole of block 3, which is quite intuitive, I guess. As for, does this observer see the topology? Well, I mean, you know, what do you mean by see, right? Of course, I mean, of course, in the past light cone, of such a, right, if you consider the past light cone of this, then, you know, there exists a missing R cross S1 in the space-time region that's covered by the past light cone. Can the observer see signals from this? Not in Kerr, at least. You know, this is just missing points in Kerr. From the point of view of topology, what you could say is just simply that if you have a curve here and you have a curve here that threads, then of course these aren't homotopically equivalent, right? But what does that mean for the point of view of the observer? It just means that one of them is being accelerated back and forth, whereas the other one is just maybe falling on a time-like geodesic trajectory.
Let me clarify one thing you said.
Yeah.
You said that this observer may not see that singularity.
Right.
So isn't that a naked singularity of some sort?
Right.
Shouldn't the observer get some signals from there or not?
Well, by see, I simply mean that, you know, sure enough, the singularity is in the past light cone of the observer, so certainly it can see it.
Yeah.
But what do you actually mean by see? I mean, what are there any signals
that
that
naked singularity that may be radiating some nonsense that will come?
Right, some nonsense. But in the Kerr space-time, this, you know, the solution is what it is. So there's nothing coming from the ring singularity in the Kerr space-time. Right.
But I suspect Eric was thinking more in terms of, you know, something weird in the past might have actual signatures at the present moment.
Yes, right. But in the Kerr space-time specifically, the metric, you know, is what it is. The observer will, you know, feel a certain amount of acceleration and whatnot. But what people tend to mean when they say, can they see the singularity, or you know, what they tend to mean is kind of a strange statement, really. What they mean is something like, you know, suppose there's a naked singularity. This is often represented like this, right? What they mean is that the solution is only determined, you know, in this region here. And what they mean is that from the point of view of this observer, you know, I could have some crazy signals, you know, coming out, some aliens, say, whatever, that are coming out from this naked singularity, and that would be perfectly consistent with a situation where the solution had been exactly the same up to the same point. So two observers can, you know, see exactly the same signals, and then if there's a naked singularity, there's a fundamental non-uniqueness past the Cauchy horizon, and therefore, yes, in principle, you could send anything out from these naked singularities that would be consistent with the solution having been in the purple region up to that point. So in that sense, yes, absolutely. You know, this is what's going on. But in the Kerr space-time, the metric just is what it is. There's no green slime. There's no aliens coming out of anywhere. You know, it's just a perfectly good, honest metric in region 3. Despite the fact, of course, that it's deeply nakedly singular. Good. Okay.
So I'm sorry, Martin. There's still one aspect of the question that I'm confused or puzzled about, and yeah. I think I have a clearer way of putting it.
Go ahead.
If I'm an observer, right now, my space-time event is on one of the spheres. So the topology is 2 spheres connected at the poles. You know,
yes, this is the picture. This is the picture. Yes, this is the entropy type.
So the way to think about, if I'm at an event that's in one of the spheres, then is it the case that every time-like path I can take that will take me through the hole into the other sphere, that necessarily takes me through the ring singularity? Is that the case?
Oh yeah, right, of course, yeah.
Excellent. Now I got it. Thank you.
Yeah. That comes from this diagram. You should be you're right. You can see this from this diagram, right? Because any curve.
Just want to make sure I was reading the diagram right.
Yeah, you're reading the diagram.
Thank you.
You're reading the diagram perfectly right. What's a more complicated question is, when I pass to the universal covering of block 3, what I'm doing is I'm unwrapping the ring. When I unwrap the ring, I change my pictorial representation of the homotopy type of the interior from something like this to something like this. And then what's very non-obvious is if I have an observer traveling in this space-time, what does the ring singularity actually look like? And the ring is no longer a ring, of course. And it's just some kind of line singularity that passes through, but that never enables for a homotopically non-trivial curve. So I can, strangely enough, I can't have a time-like trajectory that ends up looping around the ring like this, because that would be a non-contractible trajectory. Whereas, if I'm traveling along here, I'm a contractible, homotopic to a point. So what's very difficult to visualize, and nobody ever does this, is the universal covering spacetime of block 3. Right, so that's something that if you're a graduate student and you've got plenty of time on your hands, try and fill up a page book of what's your best representation of the universal covering of the Kerr interior. I challenge you to do that. It's quite a fun exercise. Pretty hard though. Okay, let's now get to part 3. So we got a lot to get through. Part 3 will be the kind of preliminary step to part 4, and this is going to be about building extensions beyond the Cauchy horizon. So of course, at the present moment, I've given you a metric, but those among you who paused on the specific forms of the metric will see that it's not defined at certain regions. And so, although there's block 1, block 2, block 3 that are kind of defined in terms of the coordinate ranges of R, so I'm going to draw it like this. Now I'm drawing a Penrose diagram here, but it's really to be taken with a pinch of salt. It's merely for the sake of exposition, and you shouldn't take it too seriously. Okay. So this is block 1. This is block 2, block 3. This is R equals infinity, R equals infinity. This is R equals R minus. This is R equals R minus. This is R equals minus infinity. This is R equals minus infinity. And this is R equals R plus. So I'm going to draw lines. So the event horizon is this. The left portion is not yet an event horizon because there's no exterior that's been attached onto it. So you shouldn't think of it as an event horizon so far, but eventually you'll see that it's the event horizon. Then this is the kind of asymptotics of region 1. So past and future null infinity, as we call it. And this is the equivalent thing in region 3, but R is allowed to take negative values here. And finally, let's draw blue. And this is the Cauchy horizon, which we haven't identified as a Cauchy horizon yet, but it will be a Cauchy horizon, as you see. Okay, and the question is, this is the metric so far that I showed you, right? So the Kerr metric in the Boyer-Lindquist coordinates actually only cover the interior of these regions, okay? They don't cover the junctures, right? They're just like in Schwarzschild, they kind of fail to be well defined on the horizons. And so you have these bulk, you have these interiors, but the question is, how do I actually glue block 1 and block 2 together so that I produce a metric which is non-singular anywhere? So we'll call this, gluing or attaching, gluing blocks, right? And the question is, how do we do this? Okay. Now, the way you do this, so I'm going to call this space-time Kerr star. Okay. And the way you do this is you select what's called principal ingoing null geodesics. And if you think about what that really means, what's really going on is you have this axis of rotation, right? This is, say, maybe you could think of this as the event horizon, say. So let's just say it's the sphere given by r equals r plus. Okay. And what we're going to do is we're going to take geodesics, right, that are kind of inwards pointing, right, and they're inwards pointing. And so if we think of the angle, right, that they make with the vertical axis, they make an angle theta. These geodesics will have the property that they're not the derivative of the curve in the gap in the theta direction is 0. Right. So these geodesics are defined by so the prime is differentiation, and these geodesics are defined as follows. So basically, you're shooting null geodesic. You're shooting light towards the black hole, but you're shooting it in such a way. You're shooting it from a sphere where you're aiming it so that theta is not changing instantaneously, at least at that point. Right. So these are your in the Boyle-Lindquist coordinates I showed you before. This is what these geodesics. These geodesics are. This is how you parameterize this geodesic. So what's going on is phi is changing, right? So they are being sent. They are varying in phi, and they're not changing in theta, however, at the sphere. And what that does is that to kind of track the evolution of this geodesics, you perform a coordinate change. So the way you tend to extend a metric beyond any kind of region is you look at the metric, you see where it seems to be going singular or it seems to be behaving strangely, and then you can think of a change of variables, which allows you to suddenly make the troublesome region disappear. And this is, of course, the famous case of Schwarzschild, where the event horizon, so on and so forth, coordinate change, etc. Same thing happens in Kerr, but it's a little more complicated. You change to a different set of coordinate system, which is based on these geodesics. And what that means is that you change, so the only variables you need to change are just t and phi. And what you do is you change them by functions, right? Big T and big A, which basically mimic the geodesics, right? So that's why these geodesics are useful. You see, the way that these geodesics come in here, the way that the differentiation of the parameters in the tangent vector, if you will, of the geodesic is exactly inspiring the coordinate change that you'll make on t and phi, right? Because these functions, you can see that they're the same, right? Okay. And when you do such a thing, when you do such a thing, it turns out you can get rid of the event horizon singularity or the event horizon, the problem at in your coordinates at the event horizon in just the same way that you did for Schwarzschild. Okay, in just the same way. So in other words, r equals r plus is no longer a singularity. It was just a bad choice of coordinates. I do need to plug in my computer, but yes, that would be good. Yes, that would be good. Sorry about that. All right, bear with me, everyone. I'm just having a battery problem here.
Just been watching and getting that.
Yeah.
Yeah.
Oh, beautiful. Oh, you've got great.
So
I actually have a charger, so I'm going to disconnect the cable for just a second. Yeah, thank you. Wait, where is this going now?
so it goes in. Oops. Oh wait, what's that?
That's your. Do you not? Are there not two ports?
No, there's only the one.
Oh, there's only one.
That needs to be connected. Doesn't it?
That needs to be connected. Let me join the Zoom from my.
I can just use my.
Maybe if you just give me your computer and then I can plug in my iPad from your computer.
Do what you want.
So I'll just charge this. Yeah, I'll just charge my laptop for the next talk. Giving another talk today. So there's lots of battery usage being done. Yeah, all I need to do is just to plug in my and then I can share screen. Thanks, Jamie.
Yeah.
Beautiful. This should work now.
Yeah.
Do I say open or just cancel?
Just go open Finder, I guess. And... Okay, I don't know how it's gonna.
Right.
Is it not allowing you to share your thing? Okay, just click cancel, I guess.
All right. I think I just have to. Maybe there'll be a. Let's try again. Oh, but this.
This is for the video, right? Just do the.
This is just for the video, yeah.
Just do the video of mine and do what you were doing before with yours. Then we've saved you a port.
Yeah. Okay. Let's do that. Let's do that.
Whatever.
Yeah. Okay. Good. Okay, ladies and gentlemen.
Was that the experience of passing through the ring singularity?
You're muted, Martin.
Hear me?
Is that better?
Hello? Can you hear?
Yes, I can hear you now. But you're muted again.
Okay. Hello? Yeah. Can you hear me? Good. Okay. Yeah.
Right. Yeah, I was just wondering to what extent is this procedure uniquely defined, or why is it that you're considering geodesics of theta constant? Let's say, I mean, you want to find a family of geodesics that pierces the R plus, right? You want to find some geodesics that go to R plus. You can consider, say, pi constant. Right? So, to what extent this procedure is defined?
To what extent is the choice canonical was the question, by the way, for everyone. The answer is it's not. It works. It's not canonical. You could find, if you gave me a more complicated set of geodesics, we could try and think of a different coordinate change, and we could try and play the same trick. It just so happens that things is very nice when you do this. But you know, what's nice about this choice is that it doesn't just extend through r equals r plus, it extends through r equals r minus, and that the geodesics take a particular simple form, and I can draw them and you can represent them easily. But just like in Schwarzschild, you know, if you find a different set of coordinates that extend through the event horizon, you know, by all means, be my guests. The same thing happens here. It just happens that, you know, this is easier to deal with.
Well, I guess this is citing the fact that these geodesics happen to the principal. These geodesics happen to the principal non-directions
Yes.
of Kerr space-time. If I take the bias tensor, these are going to be one of the agent vectors.
Absolutely, yeah. They're kind of they're nice, yeah. They're good coordinates.
These are precisely the one that Kerr used in the original.
Yeah.
In the original coordinate.
Yeah. In the original diagram. Yes.
This coordinate. So okay, that's it. My question is just some what's the notion that you use to come up with these coordinates where theta is fixed constant and not phi, from this perspective? Or you just propose it?
You just propose it. It happens to be, I mean, you know, if I give you a solution that and it has some symmetries, there will be like specific choices that are good choices, that are natural choices with respect to the solution. This is exactly what's going on here. This is, you know, principal, null frame, and so on, where things take particularly simple form. But mathematically, there's, you know, I could have come up with a different choice and try and perform the same game.
Okay, so there's no reason for
there's no a priori reason why this is the right coordinate change to do, but there is, you know, there is a sense in which these coordinates and these geodesics, they lead to a particular form when you express things in a particular way, where things take a particularly simple form.
But geodesics with phi constant also have a closed form. I guess that this is more related to Peter's questions, because
Geodesics with what?
with phi constant.
I don't think you can have.
No, you can't have phi constant everywhere, right? Because in the ergo region near the event horizon, you won't be able to just get phi constant everywhere. In particular, once you go through into region 2, there'll be some rotation.
Right.
Geodesics with phi constant don't exist there. So these are kind of special, but you know, if you added some extra things, you could try and play the same game. It would just be harder. I'm afraid I need the toilet, so just 1 second. So yeah.
What does principal mean in this context?
it means that you're selecting null geodesics, which when you contract certain components of Weil or Riemann with these geodesics, you get some simplified form. You get some eigenvectors, or you get something like this.
Yeah, you need to compute the lightness.
So schematically, I think it's at this point I want to introduce you another diagram where we're going to do block 1 and 2 and 3 again, but drawn slightly differently. And I think this is useful, and this outlines one of the strange properties in Kerr that you're about to see. Okay, so what I'm going to draw now are geodesics right which are the ingoing and outgoing geodesics and what you'll see is very strange, actually. Okay, so this is the future light cone. Okay, so this is these are in and outgoing null geodesics. So these ones are ingoing, and this is outgoing. So this is outgoing, and this is ingoing. And what's remarkable is that the outgoing null geodesics, right? If I draw this closer, what happens is that these outgoing null geodesics never actually reach this point, which is r equals r minus, and this is r equals r plus. So you see that as I take these points of these light cones closer and closer to r equals r minus, and I send null geodesics which are outgoing. So remember, in the picture that we've been drawing throughout the mini series, we have something like this, right? And we have the ring, etc. What I'm drawing here is a null geodesic that's arbitrarily close to r equals r minus. So it's not even at r equals 0, right? This is r equals r minus, right? It's arbitrarily close to r equals r minus. And when I shoot an outgoing null geodesic towards r equals r minus, somehow, because I'm past r equals r minus, the outgoing null geodesic never makes it to r equals r minus. So if r equals r minus is the center of the black hole, the center of the Kerr black hole, if you will, it's almost as though the passing this horizon has changed the sign of gravity. Gravity becomes repulsive somehow. You see, these null geodesics they're arbitrarily close to r equals r minus, so they're really, really, really close to here, and they're being sent outgoing, right? They're being sent away from the ring, and yet because of the way that the light cones are organized at this point, they never actually make it to r equals r minus, And this is something you can't really see in the Penrose diagram, because in the Penrose diagram, you would just draw these geodesics here, right, in region 3, and you would just, draw them outgoing, and you would just think of them as kind of the same as these kinds of geodesics. But actually, that's where the intuition, just based on the Penrose diagram, kind of fails us, because when you actually look at the kind of light cone structure, where the magic of the conformal factors kind of disappear, you don't see this effect. So yeah.
This is exactly the same for Reisner-Nordstrom as well, right?
Yeah.
So in this respect, they really are the same problem.
Yeah, it seems that once you pass the Cauchy Horizon, somehow geodesics aren't behaving in the same way as they would be outside or even inside the black hole. Okay, so now let's see, how long do I have left? Oh dear, it's going to be tight. Well, I guess I'll finish next time. I'm going to stop 5 minutes before, because I have another talk to give, so I must be a little careful with my energy. But essentially, what I just drew here of these, right, this Kerr star, I can do something similar, but with what you can call star Kerr, where essentially, rather than taking the ingoing ones, you take the outgoing ones, but you start from block 3. Right, you start from block 3, and then so the geodesics are almost the same. So but the coordinate transformation is a little different. So it's just, of course, it turns out that these star Kerr and Kerr star are isometric, but they're kind of, to think of it, this is equal to Kerr star run in reverse, where I change the time direction, so change t and phi, right? So that in one case I have a black hole that's rotating like this, and the time is going up. In the other case, I have a space-time that's going like that, and the time is going down. There's an isometry between these things. It's like running a movie backwards. The actual metric is the same. Well, it's isometric, so I can find a coordinate change which maps it onto itself. R and theta stay the same. Okay. Now, when I do this, right? Something happens which is important. So I'm gonna draw these like this. So this is Kerr star. So 1, 2, 3, and this is star Kerr. And star Kerr looks like 3, 2, 1. Okay. So now what I can do is I can flip star Kerr, right? So that it becomes like this. So it's just another isometry of star Kerr, right? I can flip it. And then what I can do is I can bring these two together. So you can call this the flipped star Kerr flip. We'll call it star Kerr prime. And then you can bring these two together. Bring these together. And what that gives you is something like this. So you start out with you start out with Kerr star, okay? So you start out with Kerr star. Okay, let me draw this a bit better. This is Kerr star. So 1, 2, 3. This is Kerr star. Okay. And then you see, I take my flipped so star Kerr prime. And then I can find a bigger space-time, which contains the two as follows. Okay, this is now star Kerr prime. And I can now view, this is now 3, 2, 1, which is just star Kerr, right? So I can add on this. And now this is star Kerr. And there is a mistake. Give me a second, there is a mistake. This is star Kerr prime. No, actually, no, there is no mistake. This is correct. This is okay. Yeah, this is okay. Okay, good, good, good. Okay, so this is good. And we've now built this by finding a bigger space-time, flipping the kind of time reversed, rotation reversed Kerr star to make star Kerr prime. But then what happens is that once we've done that, we can identify, well, we can glue on star Kerr prime to Kerr star by playing the same trick that we played with the coordinate changes, but now in these directions.
That's the one that's not clear to me. But
Yeah.
you can't simply paste, right? There should be some rules you have to follow.
Yes.
Okay, how do I know that this is allowed?
The horizons match. There exists, once you do this, you what you find is that so you have two metrics and there's an isometry between them, but the isometry flips the time and the phi directions.
Because of the flip you are allowed.
Because yeah, exactly. And because of the flip, I can join up. So this is already a flipped version of this, right? In the time and the phi direction. And then this is a further flip of this in the, in the ingoing, outgoing way, okay? And then once you do that, you can find something that's globally compatible across this patch. Once you've built this, once you have this guy, then you repeat the operation. You repeat the operation and you end up with the diagram, which is this one, right? Right, the one you know. Right, where you have these regions like this. Now, you still actually haven't, it's still not over because I've lied to you throughout this whole process because there's something singular that happens at the coordinate changes in these crossing spheres. These crossing spheres are, say, r equals r minus, r equals r plus. And at these crossing spheres, the coordinate changes and everything actually don't work. So you still haven't covered those crossing spheres. And for this, you need to do a same Kruskal type extension that you did for Schwarzschild, but you do it in this context. So what you do is you come up with U So plus and minus are just going to correspond to these crossing spheres, which are different. And then these is V star plus theta never changes, and then phi plus and minus, where kappa plus and minus is R plus minus minus R minus plus over 2 R plus minus minus A plus A squared. And then U takes the same form kind of in the Kruskal, right? So you kind of exponentiate it. And now you have these functions. And with this change of coordinates, furthermore, you can show that whoops. Right. So the diagram I drew so far, that if you look in detail at what happens at the junctures of these things, you have a failure in the coordinate changes and in the metric there. And so just like in Schwarzschild, you need to come up with Kruskal, but in this context, but the Kruskal extension looks different whether or not it's the event horizon crossing sphere with the past event horizon crossing sphere, or if it's the Cauchy Horizon crossing spheres. And this, if you remember your Kruskal coordinate changes in Schwarzschild, they have the same kind of form. It's an exponential with a constant factor in the exponential time the t variable. You do the same thing in here, but then it's a very non-trivial calculation to show that this now covers these whole patches. Right, these whole patches. And that I can't do the calculation for you in the time given. I mean, it's multiple pages. They were found, by the way, by Boyer-Lindquist. So Boyer-Lindquist were aware of this. They called them Schwarzschild-like because it was Kruskal-like. People call them now Kruskal Boyer-Lindquist, or BKL sometimes. Okay, so I was going to make some additional comments. But given the time, I think it's time we maybe try and have a couple of questions. Yeah, Eric is making a kind of pun joke type thing.
Oh, that Eric.
Yeah. Okay, so essentially, yeah, you're using the key. I think the key observation is you inspire a coordinate change on the basis of a specific choice of geodesics, the principal null and the ingoing and outgoing, which are constant in theta. You use these to go through the interfaces of block 1 and 2 and 3. What you end up with is two different versions of this procedure. One that starts with block 1 and goes with the ingoing. One that starts with block 3 and does the outgoing. You could think of them as being reversed in the time direction. So you think of ingoing towards the future, outgoing towards the past. Then you write down the metric in this coordinate system, you get two different metrics, but actually it turns out they're isometric because they're the kind of time reverse, angle reverse versions of each other. You can flip one of these and patch them up by using the fact that star Kerr is a time flipped version of Kerr star. Then you can continue on this patching by viewing the kind of symmetry in the diagram. And then you can finish the picture by making sure your coordinate system is well defined in the crossing spheres, but that demands a further Kruskal type coordinate change. And the final picture is the one you see, the Penrose diagram is the one you see, modulo the comment about the topology of region 3, which has all the beautiful and exotic things that we saw before.
Does this diagram imply that every point topologically a sphere?
No. Right, we went through this. You weren't here in part 2. You can follow on YouTube, but no, the interiors has a different topology. This was covered in the previous talks. It's yeah.
In the exterior, every point is a sphere.
Oh, in the exterior, in region 1, yeah, absolutely. Yeah. All right, so the interior, you know, I mean, those who have been here throughout the seminar will be, you know, will be bored to death by this, you know, diagram. But this is maybe my favorite diagram of Kerr, which is this one, which is the homotopy type of the interior, where you can see that the actual topology of the interior is two S2s that are linked at their north and south pole. And the way to do that, the way to view that is to think of a man or a woman that's blowing into a bicycle tire, and the bicycle tower is now going to hug the ring singularity. And what happens is that when you do that, you eventually, this inner radius gets large enough that you can just, you know, you could think of it as a sphere being linked by a north and south pole. All right, well, it's time, ladies and gentlemen. Thank you very much for sitting on part 3. And in part 4, we'll go in a bit more detail. I'll add some, I think, very interesting things I didn't have time to do today. And of course, we'll get to the essence of this mini series, which is the foundationally interesting questions about these extensions, what we don't know about them. And as you will be, I hope, surprised to see, is that we don't know very, very basic and important questions we just don't know about these extensions. Thank you.
I suggest we take 5 minutes, even though